So, dear students, let us start with the topic of energy and its type in continuation to our work, energy, and power. So, about energy, we all might have studied in our early classes that energy is defined basically as the ability to do work. So, energy is the ability to do work. We can keep down a note. Or technically, we can also say that energy is required, or what is required for work to be what? To be carried out. Now, students need to be careful about the definition of energy because there are also conditions when we talk about energy, and we can also relate it with work. We said in our previous slide or previous video now, work was defined as transfer of energy. So from there, we can conclude that for work to be done, energy is required. So that's another important point we can keep down. Energy is required for work to be done. So, and about that, we can also note that if you need an energy to generate a force which is needed to do work. Remember, we've talked in the previous slide that work is given by the product of force and the displacement, which you can write in dot product as F dot S of Fs theta. Now, about this, before a force is generated, because we need to understand the concept of a force very carefully, energy and work, because these three things are very, very important in human life. And when you talk about force, you need an energy to generate a force, like I said, and that energy is required to do work. Because without force and distance, work cannot be carried out. So not to waste our time, because this is just a slide on introduction, we can also put down in mind that under the types of energy, we say we classify energy. Energy is classified in two categories. So when we talk about categories or types of energy, we can say there are two categories of energy, which I believe from our early classes also we might have studied. The first type of energy we talk about in physics is what we call the kinetic energy. And in our junior classes, I know most of us might have studied these. And when we talk about kinetic energy in physics, we're talking about energy that is due to motion of a body. And generally, in junior classes, the kinetic energy you denote by Ke is given by the simple formula of half mv squared, which is very, very correct. Another type of energy we might have come across is what we call the potential energy, which is the second type of energy called potential energy. Now, about potential energy, we can say this is what we call a stored form of energy. Basically, in junior class, you can say the type of energy that is formed due to what? Energy due to rest is also very good. And in junior classes with the potential energy, remember, we said we denote by U is given as mgh. Now, about potential energy, there are lots of things we are still going to talk about potential energy in this slide and in the understanding of energy and other things and classification of forces based on what is being transferred onto them. So the point now is that in classification of energy, you classify energy into two categories, and the combination of this energy from junior classes you call mechanical energy. And again, another important point on this introduction slide, which we can also talk about, is there is another type of energy, which is the last type of energy I think I need to talk about, is called the what? Another type of energy, which I will take as a separate form, we call dissipated energy. Now, when we say dissipated energy, students need to understand this very carefully, because I know most of you understand what we call the law of conservation of energy in junior classes, that energy can be conserved, that is, it can be transferred from one form to another. Now, when we talk about dissipated energy, I know very well you guys are saying, okay, there are other type of energy. Yeah, other type of energy are what we classify as dissipated energy. Now, how are they formed? Because we need to understand the concept very well. Now, we can write something about dissipated energy, that these are energies, or we say energies that can never be retrieved back. Energy that can never be retrieved back after being lost to the surrounding. So this form of energy that can never be retrieved back after it has been lost to the surrounding is called dissipated form of energy. And when we talk about dissipated form of energy, examples include you have heat, you have light, you have other type of energy you can think about are classified under this. Remember, when we started the topic of work, we said work is transfer of energy. So energy is transferred to do work. Now, this energy that is transferring to do work can be positive form and can be negative form, which I'm still going to explain in the later chapter of this slide. Now, we understand from work that work can be positive when work is done by the body, and work can be negative when work is done on the body. As a result of what we talk about, when the body is doing work, we said the body is what is giving out what is supplying energy. And when another body is doing work on the body, we said the body is gaining energy, which we have explained before. So this also is going to help us to understand the concept of energy very well, because in our junior classes, we have studied a lot about energy, but now we want to take it to another level, which is needed according to the syllabus of those that are doing A-level exam, which is popularly IGMB or the JUPEP. So we need to understand that energy transformation, or in terms of dissipation of energy, we are talking about energy that is lost to the surrounding as a result of fusion. I can give an illustration. For example, we said when we talk about the forms of energy, or we talk about types of energy, I said you can only classify types of energy into what? Into two categories. Sorry about that. Now, when we talk about that, we said we have energy. Generally, energy is can be of two types. It's either it is kinetic energy, or it is what? Potential energy. Now, this energy that is kinetic or potential energy can be said to be a stored form of energy, because they are stored in the body. Now, kinetic energy is stored from, right? Potential energy is the stored form of energy. Kinetic energy is energy due to motion. So these two types of energy can be conserved. Now, but there is another type of energy which they are not doing what? They cannot be conserved. Or basically, let me put it in a simple way, not cannot be conserved. This we can say they can never be retrieved back. That is the word, when they have been lost to the surrounding. A very good example is friction, which we are going to talk more about in the later part of the chapter. So if we understand this very well, I said the other type of energy is now the one that when lost here now, which is dissipation energy. So we need to keep this at the back of our mind everywhere we go, so that we won't forget that dissipated form of energy are those ones that cannot be retrieved back. So if you understand what I've explained before, I said we have a block like this on a rough surface as this force. Because of that, a force was applied by a boy, as usual, stretching out the hand to apply a force of F on this body, and to pull this to a distance of, maybe we say distance of delta x. as this block has been pulled to a distance of delta x by the application of force, there will be a restoring force, or there will be a frictional force that acts between the block and the ground. We have talked about normal reaction, which is going to act here. We know that the weight of this block is mg every time we talk about weight acting downward. And also frictional force tends to come to oppose this motion, which is acting on the what? You can see the block, but the frictional force is doing work too, because it's also covering distance. So it's also a force. So we say the total frictional force here is given as a mu n, or you say mu mg, where mu is the coefficient of friction. You might have studied under our friction chapter. So now we can say here that this type of energy now that is lost as a result of friction will be lost to the surrounding. And those energy that is lost to the surrounding can never be retrieved back. In this type of situation, because of the interaction between the ground, which is full of interlocks and different intermolecular forces, which generate normal reaction. And normal reaction, we said, is mg, which balances out the weight, and reacting by the coefficient of friction, where we can say generally this will generate a type of energy you call heat energy. So friction is generating a force, which is equal to mu mg. This particular type of what energy, because this is the force, and work is being done by what? By the what? By the body, or it's being done on the body, which is something as what? Force times what? The displacement. Remember, the force here is mu mg, and it is lost to the surrounding, which cannot be retrieved again. This form of energy in what physics are called distributed energy. So I hope you understand this as part of the introduction to energy. As we move further in the explanation of all other categories of energy and what we need to understand on this part, I believe we are going to get a better. So let's move to the next slide. Good. About the next slide here, we have a classification of forces based on energy. Now, we can put down a note, as we have studied, that energy is the ability to do work, and you require force for what? For you to generate what? An energy that will be transferred to work. I hope you understand that statement. Now, what I'm saying, my dear student, is that based on, we can just write, based on the type of forces transferred or supplied to do work, we classify based on the type of forces supplied to do work, we classify forces into two categories. So very important for students to know that categories, like I said it is very important for students to know that the type of, based on the type of energy that is what that is supplied. I'm getting it now. So it depends on, I said, based on the type of forces that is supplied to generate energy. For example, like I said, force is required. For you to have force, there must be some energy in you. If you don't have energy, so this type of force we use to what? To actually what? To generate what? You have the force that is supplied based what? To create energy to do work. Let me break it down a little bit. Work is the transfer of energy. There are different types of energy that can be transferred to do work. And this energy depends on the type of force also that is required to get that energy. Energy is transferred into work. Forces is required for energy. I get it. So based on the force that is required for energy to be supplied to do work, we classify forces based on energy transfer in two categories. The first type of what force we need to keep in mind is what we call conservative forces. And the second type we also classify is what we call the non-conservative forces. So keep these two at the back of your mind, because it is very important to understand these two, that forces are classified into two when we relate them with respect to energy. Now, to understand this very well, we can give definition to each of these and make sure we keep it at the back of our mind. Now, about the first type of forces we call the conservative forces, we can say from the word conservation, which I believe from our grammar class, it is a preservation. Now, when we say conservative forces, we can say these are forces that stored what? Potential energy. Or we can say, I think it is better for us to put that down, but we said conservative forces are those. Let's write it in this form. I think it will be better because of definition, for example. They are forces, or they are those that do not lose energy in any form, or those that do not, I think the best English would be dissipate. Please mind my spelling. It is always what, sometimes it might be because I'm writing on a writing tab. So those ones that never dissipate energy. As we have already studied that energy can be dissipated in form of heat, sun, light, and so other form of energy, which we are still going to just talk about very well under the chapter of thermodynamics. Now, for now, we are limiting ourselves to what is required in the syllabus. So any type of force that is supplying energy and cannot dissipate, such we call conservative forces. Now, another point we can also write about conservative forces, which I think is also important for future uses, is that another important point we can keep as a note is that they never lost energy. We have talked about that they never dissipate energy. We can also see when we talk about conservative energy, they store potential energy. That's another point we need to understand. So conservative forces generally depends on the potential energy of the body. Now, the term potential energy we are talking about is that, or you can say they depend on the potential energy of the body. So what I mean by potential energy, we say potential energy is the stored form of energy. So in conservative, another important point I think I need to talk about to understand, we can say they store, or you can say they depend on potential energy, because they have this store form of potential energy in there, which they stored. Now, to understand this very well, we need to understand another important concept, which we call the conservative field. Now, when we talk about conservative field, we are talking about a region or a particular site or a particular area in which conservative forces has been stored. So I think maybe we should put down a note on that to understand the conservative force. We can say there's another time we call conservative fields, so which we can define as a region where conservative force are stored. So I would say, when we say where conservative forces are stored, that means, and we talk about conservative forces as those that stored potential energy in them, or that depends on potential energy. So now what we are trying to say is that if we are supplying a force to do work, as we are supplying that particular force, or a conservative force to do work, that particular force we are supplying is going to be converted from what we have studied. Now we have a force that we are supplying. As we are supplying the force, what happens to the potential energy? Potential energy will reduce. I hope you understand. You are trying to push something, or you are applying a force on a body, the body might start moving from one point to another. As the body starts moving, the potential form of energy will will go down. So we can also put down a note. Another point on conservative forces, which might be important for future use, is that when force is applied, when conservative force is applied, that's another point I think is good. Conservative force is applied. When conservative force is applied, the potential energy, PE, decreased. Now, what are we so studying this, and why do we need to study this? Because it's also in the part of our syllabus which we are trying to cover. So talking about conservative forces, like I said, when you try to apply conservative force in the body, as you try to do that, the potential energy tends to go down. So like I said, when we talk about conservative field, it is just a region where the conservative forces are being stored. A very good example, we are going to still illustrate that, but I'm still trying to list out points about conservative force, which students need to keep at the back of their mind. So be that as it may, another important point I think we can write is what conservative forces only depend on the potential energy in the conservative field. They only depend on potential energy in the conservative field and do not depend on the path. Now, what am I trying to say here, my dear student? Let us quickly pull in something different and see another what we have been trying to talk about. Let's say we have a region which we call a region of conservative field, and we have 2 points inside the conservative field. I call point A and point B. Maybe we have a particular material. This is point A, like I said, and this is point B. So we have a particular material or an object that is placed in the conservative field that is moving from point A. As you can see, my dear student, I hope you can see, that's moving from point A to point B. So what we are trying to say at point A, we have the potential energy at point A is UA, and the potential energy at point B is UB. So what we are trying to say now is that the work done in moving this, that is the work done, we talk about force, we know because it's moving through a distance. So conservative forces depends on the potential energy and not the path. This is the path in which this thing is moving. So if we want to calculate the energy required for this particular body now, the work done required for this body to move from part A to part B, we said the work done in conservative field, conservative forces or work done is only going to be the difference between the paths, because we are moving this from the point of UA minus UB. So students need to keep this at the back of their mind, that in conservative field, the amount of work done in moving an object from one point to another, or the forces required to move it, depends only on on potential energy and not on the path in which they travel. So work done in conservative field, because they are storing potential energy, depend on potential energy. The forces as well depend on potential energy. As we know, force is a product of work is a product of force and displacement. Now, my point now is that whenever you are asked to calculate work done in a conservative field, you should always keep it at the back of your mind that it is given by what? Difference in the potential energy from where it starts minus where it stops. Like I said, as you start to supply energy, to supply force to the body, what happens? There's a decrease in potential energy. So you are taking it as what? Initial points to the final point. But note, I think another important thing you can take a note on is that to calculate the work done, by an external agent, to calculate the work done by an external agent, we use the work done in conservative field by an external agent. We use UB, in this case, minus what? UA. Now, the question is, why is it UB minus UA? If an external agent is coming and applying force in this direction, as we say, we know the external agent is coming to apply force on the body. And when the force is now applied on the body to move it from point A to point B, what we are trying to say is that what the final work done by the external agent is the final potential energy minus the initial potential energy. But the work done by the body moving from UA to UB is from the initial point. As I've said, the moment you apply force, there's a decrease in potential energy in conservative field. So note that if the force is applied by external agent, what it means is what? External agent can either supply energy or gain energy. Please note that. So for the external agent to gain energy, we have talked about work done and how to get it. That means the value of UB minus UA is negative. So that means the person is not supplying energy, is gaining. So always keep that back of your mind. The most technical thing is what? To calculate work done by this formula in conservative field, when body is being applied, but when force is applied by an external agent, and when force is applied, when force is applied by the body. So keep that at the back of your mind, because a lot of numericals can come in there. And talking about conservative field, this is what we need to have to keep in mind. And the other type of what field, which we call the non-conservative field, which we need to talk about. Let me quickly just tell you that these never store what they never store. That's just the important thing. They never store potential energy in them, as all the energy is being lost during the process. So as we have already studied that energy form based on forces are in two types: conservative form of energy and non-conservative form of energy. So if you talk about conservative form of energy, we're talking about those that store PE, and the work done on them is always initial minus final. But if an external agent is doing work on what? On conservative field, we take the final minus initial. These are small things you need to understand. But we are trying to explain the concept. And why is it so? We said body is doing work. If external agent is doing work on the body, definitely it will be the final work minus initial work. So these are things you need to keep in mind. And for non-conservative forces, we never talk about what? Any form of potential energy, because they don't store potential energy in them. All energy has been lost to the surrounding. A very good example, like I said, is friction. So keep it at the back of your mind and don't make a mistake when you are being asked, when you are being asked about definition of both conservative form of energy and non-conservative form of energy. And again, another important point I think I can also talk about before I move on from this slide or move away from this slide, which is also quite important, is for you students to understand that when you talk about conservative forces, as you need to keep it in mind, conservative forces in conservative field is given by formula. I think we need to write that down also. We give that formula mode of the U by dx I cap. For now, I will just limit it to this. As you know, the U is potential energy and the S is what the distance covered from these 2 points. What we are trying to do is just from work done. Energy, which is equals to the same thing as work done. We are going to talk about what is displayed at my back right now, work energy theorem, I think in the next slide. Now, energy, which we call U, is equals to a stored form of work. It's the same thing as saying force times the distance. So why we are using what mode form or modular form, you can always understand, because it can be what positive what or negative. But in calculation, we use mode form, which we assume the value to be positive. So keep that in mind, that the force in conservative field is given by mode of what the U by the S I cap. Can also be a very important formula we are still going to use, I guess, maybe later in the study of what? Power, or later in the study of energy, of calculations related to conservative forces, which we can apply directly to get our answer. I believe students have watched our vector video online, and that is why I won't be talking about I cap, is X, J cap is Y, and K cap is Z. All these we've talked about in the concept of vector. So see you guys in the next slide. Let's quickly talk about the next one, because we still have a long way to go. Fine. Like I said, the next chapter is going to talk about our work energy theorem. And when we talk about work energy theorem, we can classify this into three forms. Yes, guys, three forms, or even more than three forms, depend on what? The type of bodies. Now, I'm going to do something. I know most of us we are aware of our conservation of energy, like I said in junior classes. The knowledge of junior classes is what I want to use to understand this concept, to explain this concept to everybody. Since energy can be conserved, that is, it can be transformed from one form to another form. So since energy can be conserved, we can say energy and work. Energy can store what? We can say work can be done in the body as a result of stored of what? Energy. We can convert work to energy. And again, another way you can look at it is work can be measured in joules, and it also can be measured in joules. Now, to understand this, I'm going to classify different bodies. I think let me just use 3 different bodies to explain the work energy theorem. So when we say work done is equals to energy, that is what we call work energy theorem. It's just an expression that relates the work done to be equals to energy. So because some of you might be saying this for the first time, we have to let you know what it means. So when you have that, you call that theorem work energy theorem. Now about that, like I said, we can consider the first type of body, which I think is important, which we call a rigid body. And under our topic of elasticity, we have talked about rigid body, and we said that there are those that can never be deformed by any application of force. And because of that, maybe we should classify some instances for understanding's sake, and for us to get this, what we're talking about, very well. So if we have a particular body, a rigid body, as like I said, when I say rigid body, you know what I mean. By rigid body, I mean those bodies that cannot be deformed. Now let's say we have a block of mass here, M1. By application of force, the block now has gained some velocity. Let's say a velocity of V1, and here it has now provided displacement. That means work is done on the body of X, and here this is the new body. We can say, let's say this is M2, and the final velocity is a V2. Since rigid body don't store any form of potential energy, force was applied to this body, and it has been displaced by distance or the displacement of X. We can say the work done by this body, the work done by this body directly, work done by the body, is just a change in kinetic energy of the body. And the change in kinetic energy already discussed, we can say the work done by the body is now equals to the energy, as you can see, which we call work energy theorem. And the kinetic energy of the body is what? Half mv squared minus what? Half mv squared. And you understand why I'm taking it, because we have 2 different cases. Excuse me. And here we can say this is the first one. We plot the same mass, but the velocities are changing. So we can just say here directly, we can just put our V1 and V2. You can factorize if you want. And this is what we talk about for rigid body. There is only a change in the kinetic energy of the body, which is equal to the work done by the body. Another case we can look at is for, maybe we talk about a system of bodies or system of particles. When we talk about system of particles, or before I talk about system of particles, maybe I should talk about how spring or strings, anyhow you call it. Now, but before system of particles, I think let's talk about spring first, so that we can move in that sequence in understanding. So for springs, or let's say for elastic body, anyhow you want to call it, the work done in elastic body is stored in form of what? Potential energy, which we have talked also under the what? Under the topic of elasticity. Strings, or you say springs, anyhow you want to do it. So to explain this one, we can take into consideration, maybe we have a string that is fixed at one particular end, and we have a force that is applied in this direction on the string, or let's say the force is applied in this direction and it is fixed in this direction. I just want to explain another different thing, which is more like what we have talked about in our other chapter. Now, here you can see, as you can see, what I'm trying to do. I'm having issues there with my writing part. Okay, fine. We have the spring is fixed by this. Force was applied by this. Let's say the direction of force applied is to compress the what? The deformation. Let's say the deformation, it was deformed by a distance of h, and the spring has now changed, let's say delta x. And we've talked from this that the work done by this, another thing is what forward for a string or for an elastic material. From what we have studied before, we said they store what, when work is done on there, they store what we call elastic potential energy. So the work done on this body, the work done on this body is equals to, you need to understand this very well, is the same thing as what? The potential energy that is stored. So, and we know that the potential energy stored in wire or spring is always given as half Fe, or you say half Kx is squared, because I use x as the distance of what? The distance, one distance was what was compressed. Even if it is expansion or compression, it's going to follow the same things. We are saying this spring is having a force constant of K. This has been talked about well under the chapter concept video about elasticity. So the work done by this body is only storing potential energy. So we can always do that, and we know formula for work done, which we've talked about, can be F dot S, it can be Fs cos theta. It can also be ordinary, what you call, if it is a variable force, integration of FdS, taking the limit from distance of x1 to x2. So the last body which I think I need to talk is different cases which we call for system of particles. So let us consider for system of particles. And in the case of system of particles, my dear student, we can have different situations. It can be mixed cases. When I say mixed cases, it means body can actually combine the first situation and the second situation together. How do they do that? Let's say we have, like we have discussed, there is a body, there is a saying, there is a spring, and the spring is having as you can see, my dear student, I hope you can see me now. How's network issue? We can continue with what we are doing. Now, as you can see, mixed cases is just combination of these two. Let me be fast with what I'm doing. So if we have a spring that is attached to a body, and the body is now what has gained some velocity as we have illustrated above, we can say the total combination of work done by the body, in order not to draw and waste your time, is just a combination of this spring now was connected to this body. This spring what has been compressed by a distance of has gained some potential energy, which is equals to half kx squared, or you say half fs. We've talked about this, and has also gained some momentum, that is kinetic energy, which is the same thing as what? Half mv squared. So what I'm trying to say is that for system of body, that is a combination of the first case and the second case, you can directly combine what the situation in the numericals will depend on the formula you are going to use. So work can be equals to energy, and when we relate work with energy, which call that particular situation or particular phenomenon the work energy theorem. So if you are asked to define work energy theorem, you can't just say there's a situation whereby forces of the body is equal to kinetic energy produced. No, it might be wrong. You understand? Because it depends not only on kinetic energy, it can also depend on potential energy. So it depends on both potential energy and kinetic energy for system of particles. For rigid body, only on the kinetic energy. For elastic body, it only depends on the potential energy. So always keep that at the back of your mind, as this also will be very important for us to use in solving numericals and illustration. I believe under the illustration chapter, maybe the student were able to compile questions. Let's see the next one, which I think should be the last slide on this concept. Now here, about the last phase of this is what we're going to talk now about now is the concept of equilibrium. Now, and about equilibrium as well, we might have studied about this in our early classes. And if not, we can still break it down for everybody to understand the concept very well. When we say a body is at equilibrium, technically, what we are saying is that the summation of all force, summation is that you say, you call it sigma in mathematics, acting on the body is equals to 0. Now, in conservative field, why I'm actually putting this under this topic is because to understand the concept, we use the concept of what conservative forces and conservative field to explain the topic of equilibrium. I know under the topic of your equilibrium on its own in the syllabus, which is not in A-level syllabus, we have to talk about it under system of particles and under this potential energy. That is why it is coming here. I know some of you in early classes have studied about equilibrium under the topic of moment of force. And under our own video course, you see it under the topic of what we call it our center of mass and system of particles. So when you see that reward, you are going to see the video concepts. All you need to know about that, they are there. So they are in two categories, which you can as well watch. Now back to what I'm saying. When we say body is at equilibrium, we say the summation of all forces acting on the body is 0. Under Newton's laws of motion, we've also talked about equilibrium of two bodies or coplanar forces and non-coplanar forces. All these we have slides on them which you can watch. Now, when forces acting on the body is 0, then we have also stated in conservative field. If you remember, I will keep it short and simple. We've also stated in conservative field that the force in the conservative field is given as mode of du by dx. Remember this, I cap, which is the force we use in conservative field. Now, for the force acting on the body to be 0, are you getting it? That means the potential energy per unit distance, let me take it in a way that everybody will understand, also what must be 0. And for this to occur, there are 3 conditions. The first condition, like I said, is let's just manage this sheet. Now, the first condition for that to occur, for the force to be 0, is when what potential energy per unit distance is maximum. The second condition you can keep in mind is when potential energy per unit distance is minimum. And the last process for this to occur is when it is what constant. Potential energy is uniform or constant. So we are going to be classifying these 3 processes now and explaining them with respect to diagram to explain the different type of equilibrium that you might have seen before in your early classes. To take the first one, when potential energy is maximum, we can just take a diagram to do some illustration. For maximum potential energy, a quick one, my dear students, because of time. Time is always not on our side, and there's always time for every video I do, according to those in terms of what the timing. So now we have for potential energy to be maximum, we are drawing the u by dx to what we graph of the u on the u against s. For minimum, we can take any graph according to our understanding, maximum or any other. So I'm just taking the curve, the maximum curve. So the diagram not drawn to scale, just to show some points which I think is very, very useful and important, especially. Now we can say that here we don't need to waste our time. At this point of maximum, when we draw a tangent line, which is just technically a straight line on top of this, you can say the rate of change of the UDS is also what? Is also, if we trace that downward, as you can see here, at that particular point, we say at maximum, which is shown, maximum point here, the UDX as a rate of change of the U potential energy with respect to rest is equals to 0. So now to understand equilibrium here, what we're also going to do is what we are going to shift the displacement maybe to the left, and to which I will take as a x minus, just an illustration, and I will shift it to the right, which I will take by. So we are just taking another position in the neighborhood of the maximum point. That is what I'm trying to do to understand the concept. Now, directly here, my dear student, what we do here is just now to get this. Now, what we can do here is just to draw a tangent line to get the slope at s plus here, which is according to what I've explained. Just draw a tangent, and when you draw a tangent now, you are going to see very well that the tangent line here is going to give you nothing but what you can see. You can even try to show the line. And you see here that this is an obtuse angle of 135, and tan 135 from your mathematics knowledge is negative. So what I'm saying is if this has been shifted to the right, we are going to have what we call a negative slope. So the UDS is shifted to the right, it's going to give us a negative slope. And when that happens, you can see the formula we are using is force F is equals to, now you can see it should be mode of negative, sorry about that, negative du by dx. Why we put negative, you can say, I told you when we are doing that it is negative, or mode return is to positive. So if you are using negative du by ds, which is the slope, in this case now, the u by ds here is negative. You can see negative times negative is going to give us positive. So we say at this particular point is the force acting on the body here, the u by ds, I cap is positive. So always keep that at the back of your mind, that when you shift to the right, you are going to have a positive value of force. But if it is other way around, which we can also do by drawing a tangent, and this time around, if we do that very carefully, if you are following this diagram not drawn to scale. So if we do that very carefully, we are going to see, according to what we have here, that the angle of the slope here is going to be positive value. And if it is positive value, what that means the slope here, which we call the u by ds, is positive. And because it's positive, as you move to the right, what we have is the force from the formula I have given to you will be plus times minus. It will still give us negative du by ds. So what I'm saying is towards the left, towards the neighborhood of the maximum point, when you move towards the left, you are going to see that the force acting on the body will be will slightly decrease, and when you move toward the right, it will slightly increase. Because of this, body, once it is at equilibrium here and try to shift to the right by a little bit and later shift to the left, what you see is the body will undergo a kind of equilibrium we call unstable equilibrium. And that is the first type of equilibrium we want to talk about. So for unstable equilibrium to occur here, we are saying that whenever the body has slightly been displaced, you can see this is the position before. I have displaced the body slightly, and because of slight displacement, the body can never return back to its initial position, because it has to move towards this right here. It will continue to move towards the left. So when small force is applied to a body, and that force slightly displaces the body, and after it has been displaced, the body cannot return back to its original position, such type of equilibrium is called unstable equilibrium. And that is only achievable at a situation whereby we have what we notice what in respect to what potential energy be maximum. So the second case, which we call case 2 directly, you can quickly do that here. For understanding sake, we have case 2 where potential energy is a minimum. So directly we can also do that and bring in our diagram as we have done in the first one. So this time around, we're going to use a different color for understanding sake. So let's say we have this and we want to draw